welcome to today's colloquium. Today we have an unusual colloquium that the speakers are father and son. So not only we have a duo in speakers, but they also have a very strong relationship between them. So let me start with his son, Tom Casey. Tom graduated from Virginia Tech in 2013, magna cum laude, in applied mathematics with studies in computer science and philosophy. His advisor is Dr. Ezra Brown. He is here in the audience, and mentor was Bob Rogers. Tom has been working as a data scientist since graduation, and he's currently working at the Personnel Data Research Institute. He's also an excellent guitarist. There we were just discussing that. His band, Surprise Attack, won the 2019 DC Lock-in contest. He was second in the regional contest, and as a result, they played the main stage at the last Lock-in festival. And now, Steve asked me not to introduce him, except to say that he is the father of Maureen, Kat, and Tom. However, I do want to introduce him a little bit, although we know him, of course, very much. He is one of our people here, and we know how much productive he is in research. He has written over 50 articles and given several invited talks. He has patents in his name on signal adaptive processing. And he has been the founding member of the editorial board for sampling theory in signal and image processing, and associate editor of the Journal of Signal and Image Processing, and various other honors. And he's, of course, an excellent teacher. We all know about his awards, and over the last several years. And I will right now open the floor to Steve and Tom.
Well, thank you all for coming. Before I share the screen, I'd like to, Aleka, thank you for that outstanding introduction, although just saying Maureen, Catherine, and Tom's dad is sufficient. 2020 was a challenging year for all of us, and it hit some of us even harder. And I think we're in a national exercise of healing from the process. But I will point out that because of lockdown situations, people who are outstanding live musicians, for example, Thomas, weren't able to play. And this left a bit of a hole in Tom's time and life. And well, I'm his dad, and I made a proposal to fill this with some mathematics. And I am very pleased to say that he, accepted the offer, and we have a story to tell, and that's what we're going to tell today. So with that, I will share my first screen, and Aleka, Tom can also share screen as well?
Mm-hmm. Yes.
Okay, excellent. So the talk, as we can all see, is the analysis of periodic point processes. And you think, well, how relevant is this to our world? And the answer is very, but this talk is really a data science talk. However, I'd like to go back to an old paper of Wigner entitled The Unreasonable Effectiveness of Mathematics, because I'd like to point out that thinking mathematically can give us insight in how to deal with data science. And one of the wonderful things I've covered, and my students in measure theory know this, that naming things is important. And I'm going to call the name of this principle that I've helped uncover in this analysis, the the structure of randomness. And this is a beautiful principle in that given data, which is generated by a seemingly random process, maybe there's an underlying structure we can extract from the set from which it's extracted. And this manifests itself in beautiful ways in this talk. The first is a probabilistic interpretation of Riemann's zeta function. Of course, we should all study the zeta function. And the second is in a equidistribution, which manifests itself in a beautiful theorem of Weyl called the Weyl equidistribution theorem. And that gets us into ergodic theory, which is also a fantastic subject. So, acknowledgements. I am currently being supported by a research grant from Patel and AFOSR, 3-year AFOSR grant. And I presented this research at a AFOSR meeting earlier this year. The simulations are all the work of Thomas, a very good data scientist. And it's really an honor for us to present these results. And we want to acknowledge our teachers.
Steve, can you go full screen on the
And
slides?
of course, yeah. All right.
View.
What?
Go into the view and full screen.
And of course, there we are. Sorry about that. Thanks, John. All right, 4 data sets. Data set 1, think of these as time of arrival or data times. And what we're doing is locating the occurrence of the event. The height is irrelevant, just assume it's always 1. Data set 2, more data. Is there a structure hidden inside of this data? Data set 3, even slightly more data. Is there a structure hidden inside of this? And our most challenging data set number 4, which was extremely sparse. I want to talk about this idea called de-interleaving. And the best way for us to visualize this is to be able to look at this central block here and imagine that we aren't able to distinguish the blue from the red. In the previous data sets, there's blue, red, and in this one, cyan, which reminds me, don't hire Tom and I as your interior decorators, as you'll see at the end of the talk. But you can't see the blue and the red. So given raw data like this, can we figure out a way to de-interleave, pull the data apart so you see the red trains and the blue trains? And the answer is yes, even in these incredibly sparse situations. Does this ever occur? Well, part of the reason the AFOSR is giving me research support for the next 3 summers and years is this is very prevalent in radar and sonar and bit synchronization in communication theory. Unreliable measurements in a communication fading channel, and we all experience zoom fade, zooming in and out, and that's a problem for my tribe, my clan, the signal processing people. We're working on that. But there's this incredible clever devices called frequency hopping spread spectrum radios that work in pairs, and they send a signal to each other and synchronize how they tune and retune all over the spectrum, so that if you are a covert listener listening from the outside, this has the appearance of noise. However, they tune and retune in sync so that inside is a message, a binary signal, or even just a human voice signal. The story is, and this is fantastic, and we can talk about this at the end, the actress Hedy Lamarr has a patent in this, and she used Tom, you'll appreciate this, player piano technology to come up with her algorithm that is in the patent. I thought that was just fantastic. But I was given the problem a few years ago of a bunch of data from a signal environment in which these radios were embedded. And all I saw was a set of event times. And they said, give this to Steve. He'll play around with it, and he's crazy. He'll come up with something. So the questions are, I assumed it was time of arrival, location of the frequency hops. I was asked, is there a period in these data sets? What is the period? Are there perchance multiple periods? If so, what are they? And then finally, hey, can you de-interleave this so that we can analyze each signal separately? And the solution I came up with over different times are two algorithms. One is called the MEA, and the other is called the EquiMEA. The MEA is for the one period data, the EquiMEA is for multiple period data, and the EquiMEA is primarily what Tom and I worked on this summer. So model. Let's assume we have single period data, and we have a set of event times, Sj, and let's model them as tau, the underlying period. The kj's are natural numbers, possibly increasing in size. That determines the gappiness or the holes in our data. The phi, well, you're not going to be so fortunate as to pick up a frequency hop as soon as you log in, start listening using your Bragg cell device. So you have to model some kind of a phase and model that as a random variable. And of course, the ultimate gremlin for signal processing people, noise. And here, noise should be thought of as jitter noise, where you're looking at a little window around the data element. And you've got to figure out a way of dealing with that. And for the noise, what we want is zero mean IID, and we assume that the A to J's have a symmetric PDF. And basically, this is a reasonable assumption. You have some idea of the frequency period, as we certainly did for the frequency hopping radios. And I could assume that the A to J noise was less than a floor, which was less than or equal to, and this is the worst boundary case, tau over 2. So in essence, and you can see my fingers here, I didn't want to have this amount of noise lean forward this way and this amount of noise from another data amount so that they crisscrossed. And then that could sort of introduce a false period. Now the data can be thought of as event times, and I'm working with engineers, and so they immediately say, well, model this as a pulse train. So I said, oh, you mean a train of direct deltas? I said, oh yeah, that's what we mean. And so I wrote down the direct deltas, they were happy. But then I also thought of a good way to explain this in terms of the missing observations. Think of a sinusoid and think of zero crossings. Now, we complex analysts are very interested in zeros and growth. It's kind of one of the fundamental things about entire functions we study all the time. And you want to think that you have a set of zero crossings, but a Maradona, soccer reference there, a Maradona hand of God has come in and scooped out a lot of the zero crossings, upwards of 90%, upwards of 99%. Now, given us the case of J's, if they're in sequence, this problem is well known to engineers usually and statisticians, usually squares. The Fourier analytic methods, which we're going to be using in the EquiMEA, Wiener's periodogram, work really well, but around 50%, and this is a theorem that's waiting, it's up here, I just need to put it through the fingers. It's like a statistical Shannon sampling Nyquist rate phenomenon, that if you subsample below Nyquist, you get aliasing. So that's what you're getting around 50%. You're getting these false outliers. And then I thought, well, that's not going to work. I need to rethink this. And at the time, I was teaching myself number theory and reading a beautiful book on the Riemann zeta function. Somehow, that helped me solve the problem. The algorithm looks quite simple. Here's the data set. all I'm going to do is replacement and subtraction. So let arrow denote the replacement, means that the value of the variable a is replaced by the current value of b. And I sort the elements in descending order, and that's when I start, set iter equal to 0. Adjoin 0 after the first iteration. Why after the first iteration? You want to get rid of the phase. Subtract adjacent elements. Do a replacement where that adjacent element becomes the adjacent element. Resort in descending order. Eliminate zeros. That's the eta not parameter. An algorithm terminates if you have only one. If not, go back to 1. Let's do it by hand. Paper and pencil. Mathematician's friend. Here's a data set with 4. Notice the adjoining the 0 after the first iteration gets rid of the phase. So here you have 2 tau, 3 tau, 3 tau, resort, so 3 tau, 3 tau, 2 tau, and now you adjoin a 0. So this will go to 0, but 3 tau, 2 tau is going to give you 1, but you have 2 tau minus 0, so 2 tau, 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 and that of course is 0. And so in 4 iterations, you produced an estimate for the number. Now there's no noise in this. We just did it by hand. There's something nice about these numbers, these 4 numbers. It's like there's some sort of, as Knuth would call it, orthogonality going on here. And we're going to take advantage of that. But of course, to err is human. But to really screw up, we mathematicians have to use computers. And so Tom and I got together and wrote estimates to kind of unearth what's going on here. So we did Monte Carlo runs, n is the number of data points, iter is the average number of iterations, and percentage miss is the average number of missing observations. And then when we came out, we labeled tau hat as our estimate, and this is the experimental standard deviation. And what we did was we used tau equal 1 so we could see what was going on easily, and a threshold value of 0.35. And here you go. No noise. With only 10 data elements, even though we had 99.99, and the reason there's not more 9s here is because I couldn't fit the table in Beamer. I mean, this goes on for a long way. We had a boatload of missing observations here. It took this many iterations to converge, but in 100 out of 100 Monte Carlo runs, we got 1 as the answer. Why 10? Well, there's 10 fingers. I don't know. Or maybe there's something deeper going on. Okay, let's take the number of elements and reduce it from 14 down to 4. And notice here, 12 and 14, 100 out of 100, got the number. At 10, oh wait, I had an outlier. We had an outlier, 2. Oh, interesting. 8, we had an outlier, also 2. 6, we had 3 outliers at 2, and at only 4 data elements, we had only 88% of the time, 6, 4, 2. Again, why 10? And what's so special about 10? There's nothing really special about 10, but there is something about 1 over 2 to the 10th. Looking at table 1, the natural question is, why 10? And that's what we address in the next section. A true, Professor Brown, a true biscuit of number theory. Okay, this is for my statistics friends, especially Professors Barone and Gerard. This is the problem I'd like to work on. What if I add noise? Keep the gap around the percentage missing kind of in the right neighborhood. But what I'm noticing is that this is always skew symmetric. And at the end, if you ask me questions, I will pretend to think like a statistician. And I came up with a beautiful distribution, and Dr. Barone, you'll like this, of Gdenko to model this. I did the Kolmogorov-Smirnov goodness of fit test, and that seems to be modeling this. So why tau hats always skew? Well, that's a question to be dealt with in the appendix if we get there. All right, why 10? Let P be the set of primes. Great quote of Kronecker. God gave us the integers. The rest is the work of man. Whereas Dr. Washington, who just wrote me a little while ago, he couldn't make it, but he would say, you know, we have the primes and the rest of the stuff we made up. And it's true. Just studying the prime numbers can lead to just a really incredibly rich academic career. And then I have to give a shout out to complex analysis. The Euler formula in 1736, where you take the Riemann zeta function and expand it in a product distribution over the primes for, of course, real value of z bigger than 1, was introduced to us at school as a joke. So this is Hardy's my great-great-great-great-grandfather mathematically, and this is kind of a great-great-great-great-uncle, and Ramanujan's one less great uncle as well. So, and of course, the Euclidean algorithm. Here we quote Dr. Knuth. Euclid's algorithm is found in book 7, proposition 1 and 2 of his Elements, circa 300 BC. We might call it the granddaddy of all algorithms because it is the oldest non-trivial algorithm that has survived to the present day. Wow. And it is still active. The EA and MEA and the EA and equi-MEA is Euclidean algorithm. Now, as a reminder, this is a division process for the integers and is based on the property that given two positive integers A and B with A greater than B, there exists two positive integers, Q for quotient and R for remainder, such that A could be a quotient of so many copies of B plus a remainder, and the remainder is between 0 inclusive and up to B. But if R is equal to 0, we say that B divides A, and that, of course, is what gives you the prime factorization, the prime breakdown. And if we apply this algorithm again and again, we get the so-called GCD, the greatest common divisor of two integers, and that's the largest integer that evenly divides both integers. Maybe that's what's going on. And of course, the fundamental theorem of arithmetic, due to Carl Friedrich Gauss, tells us that every positive integer can be written uniquely as a product of primes, with the prime factors in the product written in the order of non-decreasing size. And if GCD AB is 1, we say that the numbers are relatively prime, but in light of the prime number theorem and the structure we now have, maybe what that means is that the two numbers do not share any prime in their prime factorization. And it's a lot more robust situation for an n-tuple than it is for just a pair. We say the GCD of K1 through Kn is the greatest common divisor of the set Kj, the product of all powers of all prime factors P that divide Kj. And then I have a little, again, example, which we can do by hand. GCD of 3 and 7, that's 1, those both primes. 3 and 6, well, 6 is 2 times 3, so you have 3. 35 and 21, that's 7. So notice each one of these pairs are not relatively prime. Notice every pair in here is not relatively prime, but the GCD of all three of them is relatively prime. That's the key to the working of the MEA. The more data elements you get, the more likely you're tending towards, as Knuth calls it, prime orthogonality. And that convergence is really quick if you look at the Riemann zeta function. Well, I'm not one to turn down a good joke. Thank you, Uncle Littlewood. So here's my joke. Given n greater than 2 randomly chosen positive integers, the probability of the GCD of K1 through Kn equals 1, that namely that they're relatively prime, is, and I know Professor Brown and Tom and other folks know this, but that's obviously equal to 1 over the Riemann zeta function evaluated at n. I don't know, both are pretty cool jokes. All right, so I read Erdős a lot, and Erdős kind of likes to formulate number theory in probabilistic ways. And I think that, I don't know, that's a powerful thinking. So let's do a heuristic argument for the theorem. given n randomly chosen positive integers by the law of large numbers, about half of them are even, a third of them are multiples of 3, and 1 over p are multiples of some prime p. So the probability that p divides k1, k2, and kn by independence is a product of those probabilities, but by the law of large numbers, this is basically 1 over p concatenated n times, and that's 1 over p to the n. Therefore, the probability that p doesn't divide that is 1 minus 1 over p to the n. You can see where I'm going with this. Put that into Euler's product representation of the zeta function, and what you have is the probability GC of k1 to kn is 1 over zeta at n. But that's heuristic. This breaks down on the first line. There is no random distribution on the positive integers. It's the very definition of a inch thick and a mile wide. Well, it's zero, it's infinitely wide and 0 thick. So, but it gives us an idea of how the zeta function plays a role in the problem. Let the cardinality of the set be given by this notation. And what I'm thinking now is a lattice in n-dimensional space of the natural numbers sitting there. And that sublattice has the coordinate c in 1 through L, but that's your n-tuple that you're after. And what I want to do is a counting argument. I want to count the number of elements in that lattice that are relatively prime. And that's how I prove the theorem. Let n sub L be the cardinality of the lattice of relatively prime elements. For n greater than 2, we have asymptotically that n sub n over L divided by L to the n is 1 over the Riemann zeta function evaluated at n. Well, this is a beautiful thing. We have enough time to look at a proof. Let this denote the floor function, and that allows me to do a counting principle so I don't have to worry about estimates for any finite, because what I can do is just let this number run, and if the prime exceeds the size of the lattice, that zeroes out. N sub L is given by this formula, so this is my counting formula, and then of course I'm an analyst, so we do a sequence of estimates. The counting formula is just the pigeonhole principle. Choose a prime number p. The number of integers in 1 through L such that p divides an element of that is the floor function of L over pi. And again, the beauty of choosing the floor function means I don't have to think about the number of primes in a lattice. And as the number theorists will say, of course, primes are very structured, but they're very unstructured. They're beautiful. But then again, you get the heuristic estimate that it's L over the floor function of L over pi to the n. Now, if pi and pj divide an integer, then each of those primes individually divide that integer. And so you can't count those twice. And so you counted them once here, counted them once here, but then you need to subtract off the pairs. Hence the alternating sign in the formula. Each one of these terms is convergent. So here's the estimate. 1 over L to the n, P1 through Pk, size lattice, that's going to be less than, removing the floor function, that's less than P1, Pk, 1 over Pi, Pk, and that's equal to the sum of Pi less than L, 1 over P to the n of the k. And this is a sum over P prime of 1 over P to the n to the k. And so I just use the easiest estimate, summing over the integers j equal 2 to infinity. And of course, thanks to Euler, we know that that's pi squared over 6. And pi squared over 6 is less than 1. And so you can use that estimate. We are, of course, in this previous thing, summing bigger than 2. So that's why we get pi squared over 6 less than 1. And so by the Weierstrass M test, or Lebesgue dominated convergence, this is going to be a convergent series. And so the series converges absolutely. And here's using geometric series to tell you what the sum of the majorands are. And then now you need to evaluate this sum. And here I will say, again, thanks to Euler, the master of us all, Dunham's beautiful book, you use the Möbius inversion formula. And that gives you the result. Fantastic. So we have this extremely, I guess you would say, an abstract result giving us insight on how to deal with data analysis. And how quickly does it converge? Why 10? Well, this is fun because I take the zeta function and I just do a little estimate that 1 is less than zeta of omega here. I'm thinking of omega now as just a real variable. And here's, the zeta function for omega greater than 1. And that's going to be less than 1 plus 1 over 2 omega, 1 over 3 omega. And what I'm going to do is do a grouping that's less than or equal to 1 over 2 omega, 1 over 2 omega for these first two. And in 4, I'm now going to go out to the 4 terms and bound them above by 4 omega, 4 copies of 4 omega. And then I'll go to 1/8 and get 8 terms and bound that by above by 8 copies of 1 over omega. But that's a geometric series. Bam. That's 2 over 2 to the omega, sum from k equals 0 to infinity raised to the k. That's 1 over 1 minus 2 over 2 omega. And there is y10. This number is really close to 1, even for omega equal 10. Moreover, this gives you a way of estimating the zeta function. So the MEA, what you're doing is you're doing the algorithm using the structure of the Euclidean algorithm generated by the equidistribution theorem to guarantee that it's working. We can always factor out a factor of tau in the GCD. And every time, and this is a key insight, every time we do the MEA, we have to get through the first iteration to get rid of the phase term. But every time we do the MEA, we preserve the GCD. And that was like, boom, that's what hit me in the head. That was the key insight of how to solve the equi-MEA problem. Combining this with the underpinning gives us why it works. The GCD of K1 tau through Kn tau is converging to tau quickly. This estimate tells you that it's going to be there with even as few as 10 data elements. Well, there's always a trade-off noise versus data elements. And so we have underlying this structure of randomness over Z. If you choose at random an n-tuple of natural numbers, it is very likely that they are orthogonal in the sense that they're relatively prime, even for as few as 10 data elements. And this will tell you, this simple little estimate will tell you that, oh, wow, I can actually, based on the number of data elements, give an answer as to how likely it is that I'm going to produce the GCD. Factoring out the tau is important, but the key lemma was, oh wait, the entire time that I'm doing the MEA, I'm preserving the GCD. And that then was, that key lemma was what told me, I was thinking about how to de-interleave. And I realized, I said to myself, you dummy, you already have it. It's just that in Weil's equidistribution theorem. First of all, the name. There's the MEA, that's the main engine. But now what we're going to do is we're going to use the equidistribution theorem to extract the periods from multiple period data. again, like the MEA, it works where other algorithms completely break down. And it's robust, but as Thomas will show us in his live demo, you're getting to the boundary where mathematics and computer science, computational science, and data science all are reliant on each other to deal with the analysis. What's the model? Well, I recall the model of data from the original one period data. And now I'm just assuming that I have M copies of that. So each one has its own phase. The Kij's correspond to the tau I. Those are the Kj's from before. And the eta ij's, that's the noise. So I'm putting this through the MEA to start with, and I'm dealing with the phi, getting rid of that by subtraction, and I'm trying to isolate the taus. Again, the phi are phases randomly distributed up to Ti. And here I made it slightly easier. I'm assuming that the 8ij's are zero mean IID Gaussian with a standard deviation 3 sigma ij less than tau over 2. That meant I'm not having this mixing problem that and this tau here is the smallest of the taus. And I'm assuming that it's because yes, you can blow this algorithm up. And so the goal then is to extract, but I'm not giving it in this form, like that de-interleaving picture. They're all just jumbled up. Hey, what's the periods, man? Find them. Weil's equidistribution theorem, ergodicity. Let phi be an irrational number. Let's compute a wrapping of phi in the sense, let's take multiples of phi and just look at its fractional part. What is the fractional part? It's the number j times phi minus the floor. So notice you're taking these things and bumping them back in to 0, 1. And then you're saying, oh, this is cool. They are filling in. And to boot, Weil's theorem says that they basically fill in uniformly over the entire interval. Wow. Or, as I'd like to draw if we actually had a blackboard, and I'll show you the picture in a second. So what I did was used the equidistribution theorem to expose a new structure of randomness, that this operator here on my data acted like Weil's equidistribution theorem, except on a set of measure 0, which were those rational numbers which are rational multiples of the tau sub I. And I was able to prove a theorem. A sequence of real random variables is essentially uniformly distributed in the sense of Weil if I could get that equidistribution theorem. And that's what I proved in a measure theoretic sense. But what's even better is this idea of where the equidistribution arises. Imagine a lattice with lattice points at the integers sitting in the upper quadrant of R squared. Now draw a ray starting at 0, 0, making an angle phi with a positive axis. If phi is irrational, you're eventually going to hit one of the lattice points. But if it's not, it's going to come close to a lattice point, but it's going to keep meandering. Moreover, now what I'm going to do is take that lattice, glue the edges, and create Homer Simpson's favorite food, a donut. And then what I'm going to see is a spreading out of those numbers. This idea goes back to Boltzmann in physics, and ergodic is an amalgam of the Greek words ergon, work, and Odo's path. So what we're doing is we're spreading out the work across the surface. Or a hand-drawn picture after my bike ride on Saturday, I said, hey, Tom, I like drew a picture. And he's like, cool. All right. So here's the lattice. Here in green is my trajectory. Now what I'm going to do is notice phi won't hit one of these lattice points if I assume it's irrational. If it does, it's going to hit a lattice point, and when I do the gluing operation I'm about to describe, the loop will be closed. So now what I'm going to do is I want to make from here Homer Simpson's favorite food. So I take the red edge and glue it to the red edge. That gets me a cylinder. And I take the blue edge and glue it to the blue edge, and that gets me, ta-da, Homer Simpson's favorite food. A trajectory, then I'm going to lift this trajectory up to the bagel or the donut. I suppose it should be a bagel. We're more health conscious these days. I guess donuts are, you know, passe. So here is a lovely bagel, plain bagel. And I'm lifting phi tilde, and in lovely Celtic green, if this is irrational, it's never going to close. And moreover, it's going to fill in with a lovely Celtic green. The patch will fill in. Moreover, the rate of fill in is tied into the continuant, the continuous fraction, and Richard's laughing here. Oh, that's why we study continuance. The continuous fraction expansion of phi if such a device exists. And that's deep work of one of my professors, Katak at Maryland. So we assume for each I, the kj is a linear increasing sequence of natural numbers, and then Weil's theorem applies asymptotically, and that this is my new theorem. For almost every choice rho in the sense of the Lebesgue measure, the phase wrapping is essentially uniformly distributed in terms of Weil. Well, this is a measurable and measure preserving mapping onto 0, 1, this beautiful Floor function fractional component mapping, and could claim for a choice of rho, this is an ergodic mapping. It's going to be that spreading property. And if I normalize TLTU to 0, 1 and assume that X is a square integrable random variable L2, of course, L2 means, hey, Fourier analysis. So I write this down in terms of a Fourier series, and X of phi is given by this recipe here where it's NT over rho. And now, oh, I'm back in the realm of the proof of Weil's equidistribution theorem. For X to be invariant, I have Cn of 1 minus X of I phi NT over rho is 0 for all n. But that tells you Cn is 0 or this equals 1. But since phi is a rational almost everywhere, remember the rationals are a set of measures 0. They're countable. The latter, this is false on a set of full measures. So you have an almost everywhere result for this. But moreover, the set of rows for which this is not true are rational multiples of Ti. And I was like, once again, bonk, hit myself on the head like Homer does. Donuts, you know, and I was like, gosh darn, I said it a little differently. I think I got the result. I phased wrap by computing the spectrum. The values of the spectrum will have peaks at the TJ and the harmonics, TJ, Thomas Joseph. And so we have a new algorithm. So here's your gluing together the copies. Basically, you do the MEA, compute the spectrum, threshold, and look for peaks. If you capture a peak, remove it and its harmonics. The estimate Ti and over M, you're going to have harmonics. Like, remember, if T is tau is a period, then so is 2 tau and 3 tau. So those harmonics show up as tau over 2, tau over 3. And so these pictures are going to have a bunch of peaks converging at the origin. Frequency notch and repeat until you have no more peaks. Does it work? Excellent. I know I went fast, but I want to save time for Tom's fantastic demo. And all these are, thank you, Thomas. Thomas's beautiful work in Python. Double level of work, because not only did he have to code it up in Python, he had to listen to his old man, at least sort of, for part of it.
That was the kicker. And then all of the code that I got delivered as an example of what I was trying to do was in MATLAB. So I had a fun time translating everything around into Python, and use the term beautiful very loosely. We'll see what they think of the color schemes that we chose.
Well, okay, like, you know, we're not interior decorators, so but you play a mean guitar, and together we make a good team of data scientists. Now go back to data set 1. That had one underlying period. There was 90% of the information was removed and 10% jitter. What we're going to do is run the equiMEA 3 times and look at the modulus of spec iter after 3 iterations. But by proceeding right to left argmax, as the engineers like to say, well, you're going to see that there's a peak at 1. So we did start out with the first data set with 1. Again, extremely sparse and jitter. There's the first data set. There's spec iter after 3 iterations. Now notice, to me, this picture is beautiful. First of all, there's the reinforcement of what I was saying in my theorem. Second, look at that. That's the equidistribution theorem at work. Wow, look at that noise. Remember, we're not distinguishing ahead of time that things come from this period or this period. We're just putting them into, it's like a, I don't know, wood chopper or something. We're putting them into the MEA and saying, oh, the data is going to come out and produce an element. And then, of course, there's 1.5, and Tom's going to chuckle because he's going to explain this. Wait, the harmonic at a third isn't so hot, but it's still there. So we frequency notch, and boom, that's 1 period data. I could then MEA it. I can tell you what the KJs are. We can bust the shift register. And the NSA has itself a beautiful algorithm for decoding in AFOSR. All right. Data set 2, again, looked like a bunch of lines. They weren't as sparse. And of course, and my students are going to laugh, of course, I wanted to do the golden mean as the second incommensurate, in the sense of rationality relationship, as a second generator for the data. 90% information removed, 10% jitter. Here's spec iter in a second. We'll see that in a second. And proceeding right to left, again, argmax is what the engineers do. The largest period occurs at the golden mean, the second at 1, and you'll see the harmonics as they march in. Then we had to de-interleave. Well, harmonic analysts know how to do this easily. Once you have the period, you do a convolution operation with a pulse train, and what'll pop out is peaks in your pulse train, and that allows you to de-interleave. And then the hardest thing for Tom and I was choosing the colors. So we'd already used blue, so we went with red for 1 and green for the golden mean. And we kind of stuck with that. There's the data set 2 from the beginning of the talk. Here's the spectrum after 2 iterations. Again, this warms my heart. Notice how beautiful the spike is at the golden mean. 1 plus the square root of 5 over 2. This has to do with the fact that the golden mean is the most poorly approximated by rationals, a theorem in Hardy and Wright. The constant is 1 over the square root of 5, and the continuant is beautiful. It's just all ones. Here's your second period. But notice, what is this? This is the golden mean over 2. So after you identify the golden mean, you frequency notch to get rid of all its harmonics. Then you're left with 1, and you frequency notch and get rid of all of its harmonics. And then you realize that's 2-period data. And then you do the convolution. And it's like Stanley Tucci's visit to Tuscany. I mean, look at that. That's just a beautiful, that's actually not bad modern art. So-so. But there you go. And then I can feed these into other analyzers and figure out what the KJs are. And the NSA is really happy because then I can bust the shift register and all kinds of things. And I get too good at this one day, the NSA will just kind of disappear me or something. The third data set had 3. The elements are 1, the square root of 5, and 7. There's the original data set. Here's the peaks. There's the square root of 7. There's the golden mean. Notice this is the harmonic, the square root of 7 over 2. So you got to get rid of that before you can identify the third peak at 1. But frequency notching is key here. And then you de-interleave, and this is definitely why you don't want to hire Tom and I, because, I mean, all right, it took us longer to come up with the colors than to do the algorithm. It was like, what's going to be the third color? And Tom goes, cyan. I said, cyan. It's like, yeah, here. And I said, oh, the Miami Dolphins. How about those Dolphins? You know, so sorry, this is bad art. Data set 4.
For high contrast. That was the thing. Needed the high contrast between the different pulses for the corresponding periods, because obviously some of them are a little close together in that view. We had justification for why the colors look so bad together, I promise.
And thank you. Data set 4 was our most recent creation. This is what we did for this talk. 99% missing observation. One of them was the square root of 3 and one was 1, but the 99% missing observations made this extremely challenging. Data set number 4, extremely sparse. There's 2 periods built in here. There's the spectrum. Notice it's not as well reinforced, and you can see this from the de-interleaving. Look how few green elements we had to work with. And this then caused problems. Now I have a technique, and Tom and I have talked about this, for expanding this for spatial processes. And that's for a future talk. But data set 2 worked beautifully. And I would like to acknowledge just how beautiful one can compute the golden mean. And here's the continuant or the continued fraction expansion. Of course, this generates the Fibonacci numbers. But maybe what we need to hear from is the insight from Tom with Python. And so I will stop sharing.
Hey guys, so yeah, I just wanted to give you a little bit of a preview on one of the big problems that we faced, which is obviously the approximation sort of issue. Just like Professor Casey said earlier, really need a computer to screw things up. And so that was kind of the problem that we noticed. So the big issue with the spectrum computation was that we were trying to simulate that computation across the real number line. But obviously the best way, we could keep decreasing the size in between sort of each of the snapshots that we make to approximate the real number line. But at the end of the day, then the data just becomes so insanely big that we can't do any processing on it anyways. So for the purposes of this demo, we settled into breaking the real number line down into increments of 10 to the negative 4. And what we're going to see is just how quickly the noise buildup problem starts to happen, and it creates a drift in the data where even across more iterations, it's becoming less clear maybe what the tau values are that generated the original data set. So I'll go ahead and start sharing. You guys let me know when you can see my screen. Good stuff. All right. So we generated this data off of, with a generator of tau equal to 1 and tau equal to the square root of 3. And this is with around 90% missing data and minimal jitter noise. You have to excuse me, I hit the wrong button there. Okay, so the first thing is just a quick preview of the data set. So here we're looking at the event times for those radio pulses, or the pulse train, as Steve was talking about it, over time. And this is just a small preview of the superset generated by tau equal to 1 and tau equal to the square root of 3. So just for fun, went ahead and ran the spectrum calculation on that raw data. One of the first things that stand out is sort of how clear it is that we've got some sort of significance around period tau equal to 1. And, you know, we can see something else going on out here, but certainly not as pronounced of a peak as we have at 1. Now what we're going to do is run this backfill process, which are the first 6 steps of the EQI-MEA.
Essentially the MEA.
And so we're taking our original pulse train and then computing the differences and adjoining that set of differences to the original raw data. And I went ahead and zoomed in on the time length here, just so you could see how quickly the data is filling in, even just through one iteration of performing the backfill operation. So then we take the spectrum calculation across that first iteration of the backfill data. We still have those very pronounced peak at around period equal to 1. And now, after the first iteration, we're seeing pretty clearly a peak around the square root of 3. And with that, we also get this bit of a peak around the square root of 3 divided by 2, square root of 3 divided by 3. And we also see the harmonics that would correspond to period tau equal to 1 over n, where n is a natural number. Now we run the backfill process again through another iteration. Again, shrinking the scale even just a little bit more to see how quickly this data is filling in. And you can see here we've got a ton of data elements at low values down here. And when we run the spectrum on that, here's where we're starting to see this issue with the drift. Now, the peaks at the square root of 3 and 1 are definitely still pronounced relative to the data, but we're starting to see all of this noise, and it's really starting to creep up, especially in this space in between 1 and the square root of 3. And what we're actually going to see when we run through another iteration of the backfills is that continuously reinforcing the data is actually making it more difficult for us to pick out these peaks and determine what the periods are. So we're going to go ahead and run that final iteration. And here's our final view of the backfilled data adjoined with previous iterations after 3 iterations. And now when we run the spectrum calculation on that, this drift that Steve was talking about becomes very, very pronounced. And that's what we're seeing here, where some of the noise in here caused by this drift, it almost appears to be peaking in the same sort of way that some of these lower harmonics are lower as we get closer to 0. And yeah, that's just the wonders of having the difficulty of, even with when we were approximating non-terminating numbers on the scale of 10 to the -4, this drift happened very drastically over the course of a few iterations, but obviously due to computational limitations, it didn't really make sense for us to be looking at a finer grain than that necessarily. And that's the end of my little preview.
And I'll say that that is a high note to end on. And so, Aleka, I guess we're open for a question or two. So
Thank you very much, Steve and Tom. Any